Hello, welcome to my talk. So this is about Erlang Distribution, UDP, and TSN. What's supposed to be TSN? Yeah, we'll explain that later. So this, I have to show this slide because we are in the SlideCon EU project, and it's a research project about computation at the edge, CRDTs, and all kinds of these interesting things. And today I'm talking about this formula, the Erlang distribution, which basically gives you like plots like this and describes the statistics of queuing problems. And it was, oh, we know this guy, kind of like runs of a programming language. Or maybe I picked the wrong slides. Maybe I take rather this ones. Let's just move this guy away. And yeah, maybe we talk about the other Erlang distribution. So we have a transparent distribution protocol. We can send messages. We can link processes transparently, monitor processes. To achieve this, we can send PIDs, which get magically translated into a representation that makes basically find the other process the way back. And it basically, besides all the fallacies of networking, it behaves like it was on your own node. Pretty cool. But there are problems. The default is a fully connected mesh. So every node connected to every else node. Doesn't sound like it would scale well. And especially if you want to use the default global process registry, this mandates this fully connected mesh because there's a workaround around the fully connected mesh that has been there for like forever. At least OTP 10 is hidden nodes. So you can connect the node and tell it basically you're hidden from this fully connected mesh thing. And then you just make a manual connection between nodes. And it doesn't do the fully connected mesh thing. Basically, this node that's hidden is out of this mechanism. And with that, you can make your own topology and could actually make other topologies and make it work. But that's all on you. That's all application specific. So you actually need to have this in your application. And that's not really what we mean with transparent protocols. Then there's another issue. That's head-of-line blocking. Head-of-line blocking means that everything goes through one TCP connection, so one pipe, all these messages. And if one process sends a large message, then every other message has to wait behind that large message in the queue until it gets transmitted, until the large message goes all through the wire and arrives at the other end, and then the smaller messages can get sent. This is even more fun if these smaller messages are the ping messages that are the live signal that the node connection is still alive, which means if you lose 4 of those, then the other node thinks, oh, this node is gone, it's dead, so let's disconnect it. And then your large message got halfway lost and all kinds of things. So this is actually not very nice. So what people have been doing is doing their own large message transport protocols. So they use Erlang distribution for kind of control plane, and if all the large data things, they have a separate TCP connection. But again, that's in the actual application, so it's not really what I understand with transparent distribution protocol. So we tried to make a prototype to fix this. This was made much more easy by the OTP team, who thankfully improved okay, I have to go one step back. There's an API there in the Erlang runtime system which allows you to plug in your own distribution protocol, your own transport. Before you had actually write the port driver and was all in C level, and that was pretty complicated. And there was some preliminary work to make the messages that are supposed to go out over the link pop up again on the Erlang level, and then you can do Erlang things and have a much easier way to actually prototype things. The actual reason they implemented this was that they now support distribution over TSN, and since the TSN is implemented in the Erlang, you need to have the message go to the Erlang level, and then you can send it over the normal TSN way. And we kind of got early access on this, and we abused it to prototype this head-of-line blocking fix that we thought about. So what you do is we need to observe the message ordering. And the ordering is between two processes. So if process A sends stuff or links stuff, all these messages are ordered and are guaranteed to arrive in the same order on node B. But what we also wanted to kind of like try out is like routing messages around in a network, and then suddenly you can get out of order if you don't have TCP connections anymore. So the first thing we did, we started to add sequence numbers. So every message in this, like A to B, like every process pair has their own set of, their own number space of sequence numbers. And every message gets numbered, and so you would actually know when they're out of order and can reorder them on the receiving end. And for that, to every message on the distribution layer, we can actually get the from PID and to PID out. The from PID is actually also something that the OTP team added for us there, thankfully, because otherwise you would only have seen the to PID, the receiving PID, and that's not enough. And we had these sequence numbers, and to actually fix head-of-line blocking, we just chop up large messages, fragmentation. So if there are messages above a certain threshold, we just chop it up into smaller messages. And because we have these numbers, we can send these interspersed. So that's the round robin. So we have queues for every stream between two processes, and we round robin between those queues and send one message each. So you get a fair every process pair gets a fair share of the bandwidth. And this results that if anybody sends a huge message, it gets chopped up and round robin in, and it only gets the share bandwidth of all process pairs. And the large message will get over slower, but the small message can get through in between. And so we did some measurements with that. The red and blue line are the actual built-in distribution. That's the blue line, and the red one is kind of a demo plugin from the OTP team, which is called GenDist TCP, which does the same thing as the built-in one, which is not going to the Erlang level, but going to the Erlang level because we wanted to know if like going through the Erlang level it substantially kind of like changes the timing or whatever. And as we can see, these are pretty parallel. There's not much difference. There's a small slowdown, and the yellow one is our anti-head-of-line blocking distribution thing with the fragmentation thing. So you could see that what we actually show here is we are sending small messages, and we are measuring the time, the inter-packet arrival time, so the inter-message arrival time in this case. So what we would see here, if you send larger and larger messages, which is the other axis, so that's the size of the other messages, the messages that disturb us. When we get larger messages, our latency goes up in the normal way, as expected. But with our fix, the latency goes up in a much more linear way. And that's kind of a cross-section against the answer to see how it distributes. That's the horizontal axis is the latency, and the height is basically the bar graph, the probability. So you see it's getting definitely better. So this went okay, and it went so okay that in OTP 22, the OTP team implemented this or something like this, not the same thing because they're not using Erlang level, but they implement these message fragmentation things. So they use this preliminary result from us to get an improvement into OTP. So that's nice because we hadn't to do it. Because initially we planned to do this also, but we were slow. They beat us to us. So if we have sequence number and fragmentation, then there's a question which was actually asked in one of my talks. Why not use UDP then? I mean, you can reorder messages, and we find out if anything is missing. So we could actually send UDP packets and just do away with TCP. And so we thought we try this out and see how well it goes. So the goals of this, like, it's an experimental thing. This is not like a full-blown implementation of the distribution protocol that I would use in production. So we want to make UDP work, but we also wanted to prototype ways of actually making different transfer protocols and see how well the API fits to other modes of transportation. And from this, we wanted to get out like ways we could actually guide the improvement of this API to make it more easy to do more general things than connection-oriented TCP connections. Because the TCP connections are pretty much built in still into it expects like one connection per node. And it expects processes reading from this connection, and that it learns that the node identity by actually having it in the connection. And also it's a little bit complicated. So this was a timing diagram we were drawing to understand how the current API works. So that's all the actors in the current API. I won't explain that. It's also printed too small. I have a simplified version of this on the next slide. So that's how the stack looks like when you do your own distribution stack. So you have basically the Erlang VM, and you have your application that goes through the Erlang kernel, and then you have your distribution module. So that's a module which you specify in the command line, and which needs to kind of like comply to a certain behavior. And then it goes, in our case, to gen UDP to send the UDP packets over. And then it goes over the network. So how does this work in a little bit more detail, but not so much detail as on the very confusing big diagram. So assuming we have two nodes, and in each node you have the kernel who is responsible for actually doing the distribution stuff, and the yellow box is our distribution module, or yours, anyone's, like the plugged-in distribution module. So what happens in the beginning is the kernel tells the distribution modules, listen, and which means they spawn an acceptor process. So the circles are processes in this case. And the acceptor process initially just sits there, and then one node wants to talk to the other node. So you basically type net ADM ping, and it wants to talk to the other node. So it triggers the connection. It does setup, and that sends a hello message to the other acceptor, and the other acceptor then tells the kernel we have something incoming. There's an incoming connection, and at the same time spawns a controller process. That's the little white dot in the green thing. And on the sending side, they also spawn a controller process. You have to spawn a controller process. So you have these two controller processes. Then the next step, the opposite kernel basically tells it back like, yeah, handshake, which goes to the controller process, which signals it. We need an input and output process now. So it spawns an input process and gets itself be the output process and sends the handshake to the other end, which basically sends it back to the kernel and says, yeah, we got the handshake. So then now the handshake is done. And what happens from then on is basically messages get transferred through this like input-output process pair. It's a process pair for efficiency reasons. With the port data. Now put data and this data are the functions that you need to implement to basically receive data and send data. So what we learned from this is doing the UDP distribution model. So we kind of like copy the connection-oriented way, and we open a separate UDP listening port for every other node. So we copy all this. We kind of like also steal the port number from EPMD. So we abuse EPMD to actually figure out a port number for the other end, because that's what EPMD does, port mapping. And we use this as a UDP port number at the same time. And and that just works, yeah. And so we also have the two processes. I'm getting confused now here. Yeah, that's about it. And the next step, I want to show you how this works. And for that, I have to replug shortly. There's not enough space up here. So I can't demo this on my iPad. So we have two windows here, a red one and a green one. And I'll just go back in history because I never can remember the line. So this is a simple test for the distribution thing. It contains the distribution protocol. It was made with rebar. And we kind of like hook into the rebar build directory. So we set the path that it actually finds, includes the bin directory where rebar put the modules. So that's the first long thing, like set up the path. And then we specify the option proto-dist. It's a little bit unfortunate now. Let me just make this a little bit longer so you can read it better. So that's the argument, and then basically tells us it wants to do distribution using the proto UDP underscore dist module. And then you set a cookie and you set your node name. So let's do this. And this proto UDP will do all this UDP thing that I just described. So that worked well, but nothing happened yet because we need a second node. So we do this here too, same thing. And we call the node not foo, but bar. But otherwise, it's the same line. So now I have a node foo and a node bar. And now I need to ping the other node to make the connection happen. Pong, it worked. Cool. And let's do a test. Let's do RPC. I hope I remember this. Let's do an RPC call to the other node. And do Erlang byte size. And as an argument, we want, we send a binary so we can actually control how large this is, like 1,000 bit binary containing all zeros. And then we make an arbitrary long timeout. So this basically needs to send the binary over and get the result back. And yeah, byte size is 128. That was easy, but that is just one packet. So let's just add zeros to this. So let's increase this by 100. So this is already more than one packet because I think we chop up the packets to like 400 bytes. So that's what goes on. So this is about already 10 packets, but I can add more zeros. I'm actually not sure if one more works. Never tested this. I crashed it. So there's a thing that this goes over the loopback interface, and the loopback interface had very limited buffering for UDP packets, and we didn't add code to catch the case when a UDP packet is kind of lost, because we need to do a node down, node up, or whatever. So the RPC now hangs and waits for an answer. So let's free it and do this again. Foo at Venus. So what's the time? I think we can make it. So one more experiment. Oh, I broke it. I broke the other end. Yeah, of course I broke the other end. Well. Don't do experiments during your demo. So I start this end, and I start this end, and now I hope I can connect them again. Yep, it still works. I didn't break it totally. And then let's like copy this more small RPC call. It still works, and let's start Wireshark and show you that's actually UDP packets on the wire. So I need to find the loopback interface here, loopback. So looking at the loopback interface here, and I do this RPC. and I see nothing. Oh, no. I actually didn't do anything. What did I do? No. So now you see some packets happened here in the small window. I think I can't really make this larger. Can you see this? So here's UDP packets. So length 495, that's us. And you can actually, you see it's a lot of zeros here. That's basically the binary. I forgot how to kind of like, you can follow the UDP stream to and fro, and then you can see that, you see the node names in there. So that's the actual distribution over UDP. Yeah, well, it's kind of a boring demo, isn't it? So let's get on with the slides. Robots are more interesting. Next time I bring a robot again. I could do a battle of robots then. But I need a different robot for. Is this already back up? Yep. Okay. So that was the demo. So making this with UDP was quite complicated, and we wanted to find out if we can make this more simple. So we were thinking about, can we make a set of behaviors which do all the nitty-gritty work, doing a custom distribution thing, and make it much more easier for everybody to experiment with distribution, implement their own distribution. The problem is that the current API with quotes is a weird mix of function calls and messages and all kinds of and callbacks, function calls, and messages. That's basically the full mix of everything. And so we are thinking about like how we can actually kind of like hide all this behind a behavior which is just done functional. And there's basically two approaches we were thinking about, or we are still thinking about. One is a high-level approach, which allows all kinds of arbitrary distribution algorithms running, which comes from top down. Basically, what does a distribution need, and then hide everything else. And the bottom-up one, the low-level one, is just hide the connection handling, make this easier to make something like the UDP, like a still kind of connection-oriented UDP work. The current UDP prototype is quite simple, similar to the TCP thing. We just added the sequence numbers, and we chopped up the fragmentation, but still it's like the same structure of like callbacks and everything. And so there were questions like how would a behavior look like that we could actually make this much more easier, the UDP thing. So that would be the low-level one. And what other models can we actually find there? So our current, we are kind of like in the path of implementing a behavior here. And so we basically have like a behavior, and you have two sets of callbacks. One that kind of replaces the acceptor process, and the other one replaces the control process. And so you would basically, within it, you get set up, and but you don't have to spawn anything. You just set up your listening thing, and with info you get your message out, the message from the opposite side, the hello, and etc. So basically all these transactions, which you really need to cut in, are shown in this thing. It's still a little bit complicated. So I had another idea how to simplify this and make it much more flexible. So what if we actually only go one direction? So there was the setup end on the one node and the incoming end on the other node. But if I have kind of like a blob, this yellow blob in the middle, which is supposed to replace everything with something totally different, then I could basically fake this as both ends get incoming connections, because for a node connection, it's only important during the setup, that the asymmetry gets kind of lost when the setup is done, because then the nodes are just symmetrically connected and they just send messages in both directions. The information gets lost, who is the initiator of the connection and the other. So why not do away with the complex thing that a node basically says, I want to talk to this node, because for that it actually needs to know the other node needs to exist, but we want to hide the thing, the existence of node names basically from the Erlang VM, not the existence. We want to have a node membership thing, a node registry, which is outside of, which is in our distribution layer. And we can then use arbitrary distributed protocols to kind of like share this set of nodes. And whenever there's a new node, basically, whenever a node learns about a new node, we just do this incoming transaction that you see here. So if these two nodes kind of like showed up at the same time, both get an incoming connection. And then in the next step, you would have these send and receive messages which would go to the transport layer, which also can be arbitrary then. So that would be a different kind of behavior, but we didn't flesh out the API for that, but I kind of like have a rough idea where this could be going. So there's a second topic, which, who knows what Ethernet TSN is? Yeah, okay, so I explain it. TSN stands for time-sensitive network, and it's a actually big set of new standards from IEEE about Ethernet. Like it's 802.1 standards. Most of them are shoved into the 802.1 big Q standard, which is about like VLAN tagging, because they abuse VLAN tags for all kinds of things. The goal is of these standards to get lower latency, to get hard real-time reliable latency, so you don't have like best effort, but you have like fixed latencies. And this is coming out of the audio-video streaming, so these are older standards. There's older standards for audio-video streaming, and they are augmented to actually improve audio-video streaming and also allow real-time control systems. And there's a big industry interested very much in this, which is the car industry, because in the car industry you have audio-video streams and you have control processes, and they want to replace everything with Ethernet. And they're doing this already. They're starting to make Ethernet. They have their own transport, they have their own physical layer, which is cheaper in a car and car compliant. And so they are pushing like 50% of the people at an Ethernet TSN conference are car people, and the other half is industrial control people. And that's mainly the half we are talking to with TSN. So you need a few core components to make this work. You need very precisely synchronized time between nodes. And there's a protocol for that. It exists for a while. It's called PTP, Precision Time Protocol. It's kind of like similar than NTP, but on a LAN. And it relies on hardware to get actually precise packet arrival time. So the actual Ethernet hardware needs to support it because you need to measure when the packet really arrives to the nanosecond. And with that, you can get nanosecond synchronization of nodes. So now all the nodes, let's assume all the nodes have a synchronized clock very precisely. And the next thing is you need some kind of scheduling and traffic shaping. You cannot just let everybody anytime send packets. That wouldn't work. And there's another thing which is kind of like for the routing and also for redundancy. You need to kind of like have more control over your path where your data flows, because like in a car, for example, this gets like this gets statically calculated once, like who sends which messages, how often, where, and then they kind of route it through to kind of like utilize the network perfectly. And basically the third part basically has subparts is reserve bandwidth along a path. Basically, you say from A to B, you have a protocol to actually say, I want to send this much packets per this time interval from A to B, and then it gets reserved. And if kind of like you run out of time there to schedule, then the reservation would either go another path or would say, no, it doesn't work. And there's fault tolerance. You can split up packets. So on the Ethernet layer 2, packets get split up, sent over different paths, and get reunited at the receiving end. And that would actually make my UDP experiment work much better, because we wouldn't have packet loss. It would have just worked. Unless we send too much packets, because then we kind of like flood the network, and that's the time scheduling is there. So this kind of like big picture, that's all the standards in this Ethernet TSN thing. So the IEEE, after a pause where kind of like networking was solved and they were kind of a little bit bored and not doing much, are very frantically cranking out new standards. The blue standards are the old audio-video broadcast standards, and the green ones are the extensions to it. I don't go into for everything there's a standard. Like it's probably best if you just look it up, because if I explain all these standards, this would be a whole talk. But I pick out one which we actually plan to use or using for other things. That's the QBV. It's somewhere in the middle here. It's no, I didn't want to go forward. I want to highlight it. So this one here. That's enhancements for scheduled traffic, and there's also QCH, cyclic queuing and forwarding. And then there's asynchronous traffic shaping. So basically, what you need to do, you need to pick the right standard to implement your application behavior. So you cannot kind of like hide layer 2, network layer 2, behind like, yeah, this is the network, the cloud, and it just works because TCP/IP makes it just work. If you go at this level, if you want this behavior, you actually need to look more like what's actually going on the network level. So let's pick out this QBV standard and see how it works. So we already have, by PTP, synchronized the clock on all the nodes. So we can rely that everybody has the same cycle. So we chop up the time into cycles, so we configure a cycle time, such and such milliseconds. And in this cycle, we have different areas for different VLAN priorities. So they use the priority in the VLAN tag. So VLAN tags have a priority included. There are 8 priorities. 0 is normal. And then you can have higher priority thing. That was for the quality of service for video streaming in the past. And then you can configure schedules that you say, okay, in the green area, we only allow VLAN tag, VLAN priority 3, and in the blue, everybody else can send. But the scheduler, the switches and the network stacks kind of block the traffic when this is the reserved traffic. And then you need to make your application send. If you really want to have very good latency and very good hard real-time performance, you tell the application what your schedule is, and you make sure it always sends in this green area, the critical stuff. And then if it goes over switches, you kind of like skew these and can make a whole schedule and make sure that the road is always clear. It's like a green wave for this packet. There's a little problem that if in the blue area, like a lower priority packet kind of like gets sent at the end of the time frame, and the packet is a little bit large and laps over into the green area, this is actually not good because it actually uses up the bandwidth for the high priority packets. So we don't want to have this. And there's an easy fix for that. So you always have a gap at the end of the thing, which is the gap of the maximum size packet that you allow. 1 MTU gap plus headers, etc. So you allow nothing to start sending in this gap. So when the green area starts, it's always free. But there's other workarounds which require more hardware. There's, for example, packet preemption. Normally, you cannot stop an Ethernet packet when it once is sending. You only can have a collision in the beginning. But there is a standard, one of these blobs, one of the green blobs, is packet preemption. If your hardware allows this, and there's upcoming hardware that does this, you can send a packet, and then when you run out of time, you just cut it off. And you can actually set it up again. So it basically auto-fragments the packet on the fly. And when the low priority packet is allowed again, you send the rest of it. And that it gets reassembled on the other end. So this is, but not all hardware supports this. So before I also mentioned like path, reservation, et cetera, to be order to reserve something along a path, you actually need to be able to know where the path is. So how do we know the path? And for that, you could use a routing protocol, for example, a link state protocol, OSPF or ISIs. And there's also a layer 2 protocol, which is Q, or I have it on the next slide. I forgot the numbers. There's too many of them. So there is a layer 2 version of this, which uses ISIs as a control plane and does and controls the switch by these routes. So this is called shortest path bridging. So the way, just a short animation or partial animation how this works. You have all these nodes, and all these nodes only know about their neighbors. So everyone knows has their little neighborhood map. And these little neighborhood maps are called link state packets. That's why it got its name, link state protocol. And then these link state packets are kind of flooded, reliably flooded over the network, which is, I didn't show, so magic happens. And the packets go, that's the state, then basically all these link state packets are sent to all the others. It's basically a gossip protocol. It is a gossip protocol. It's flooded to all the other nodes until everybody knows about everybody. And then when you have all these packets, you can actually join them together, and then every node has a little picture of the whole network graph. And that's a big difference to like a normal switch, which doesn't have a picture of the whole network graph. It just switches off ports until only a spanning tree is left, which means that you don't use a lot of these interconnections. So it's not very efficient. And that's shortest path bridging. That's supposed to be the next generation of bridges. It's already used in provider networks to kind of like tunnel through your traffic. So that's AQ it was, shortest path bridging. Yeah, it's extensible, and the interesting thing for Erlang distribution here is if you use the ISIS layer, which you do for shortest path bridging anyway, you have type length value triples, which the whole protocol is made out of, and you can add your own. So you can add own data types with an arbitrary length. And so the idea we have is, got stuck in the animation. The idea is that we kind of like can do parts of the yellow cloud you saw far before in the routing protocol. So we could do node discovery, EPMD replacement, and the global process registry, even if you don't overdo it. If you overdo it and register lots of processes and remove it, don't do this. That wouldn't work well. This is only for occasional changes. So we could use TLVs for all of those. And then our routing protocol, our network layer, already knows about all the Erlang nodes. And from that, you make these connections, and then you can have an arbitrary transport. You can send UDP packets over a reliable UDP channel, or you could store and forward messages, basically only send messages to your neighboring nodes over a predefined topology to multiple hops, which you also can do because you have sequence numbers. Sequence numbers allow all kinds of things, and so they're quite useful. This gets me to the end. So the UDP prototype is working successfully, except if you send too much stuff, then it kind of like dies in the fire. Or actually dies pretty quiet. So this was a proof of concept. It proves it can be done. The code is somewhere in our GitHub, but it's not for production. This is experimental stuff. We try out things there. So what we also do is we implement a TSN switch with shortest path bridging for a customer. So that's how we kind of like got into these routing protocol things. So we are basically building a test bed for doing this kind of like outlook that you do the node mapping in ISIs and have your switches know about the nodes basically. So future work, connection-oriented UDP, yeah, maybe we go further with this. There's also Quick. Quick is basically the prototype for HTTP 3, and it also uses UDP and has like multiple channels that it tunnels through. It's a little bit like SCTP, but more modern, and it runs over TLS, and it goes through firewalls when it's kind of like more widespread. So that might be an interesting way to globally connect Erlang networks via this protocol efficiently. Yeah, you could have virtual node connections that you basically do up and down and time out That's one experiment we want to do. And we definitely want to do this TSN experiment. We want to actually run this UDP over TSN and see how it works and how well this behaves. It's kind of like interplays. We are also playing with ways to allow hard real-time processes on the Erlang VM. So not only soft real-time, but hard real-time with deadlines. And that would be nice if we would have a hard real-time distribution layer to support this. Because then we could do hard real-time distributed applications. And well, since we do control systems, we would find this pretty cool if we could do this. This leads me to another thing. If you want to have like hard real-time Erlang processes, we need a hard real-time operating system. And you might have heard of the GRisp project. The board I'm running around with around my neck, that was GRisp version 1. We're making GRisp version 2. And before the conference, we started, luckily, the Kickstarter. And you can go fund us. You can also chip in $1, and then you get all our updates for free. And that leads me to questions.
So I'm curious if you ran any performance tests comparing TCP and a UDP distribution.
Not yet.
Okay.
We were lucky it worked.
Okay.
Oh, we're happy.
Thank you.
We just made it work before the conference. And it only kind of works. If you send a lot of, so the performance test would require that we would send huge binaries, a lot of them. And since it always crashes, the performance would not be very good.
It would be also interesting to see small messages.
Small message, yes. We will definitely do that, probably to be presented at a future conference.
Thank you.
Could I ask whether for maybe mobile applications or applications that traverse networks, whether other protocols like SCTP would be fruitful areas of study?
There is actually an SCTP prototype out on the network with the new, when the new distribution layer came up, Tristan from Rebar 3 made a little prototype with SCTP. And of course, SCTP would be an interesting protocol for that, because there you have your separate channel and you would map the process pairs to SCTP. Are they called channels in SCTP? I forgot. Associations, yes, I was missing the word. So you can basically map each process pair into its own association, and then it would actually also fix all these problems. Definitely yes.
More questions? All right, thank you. We'll be doing the next talk in just a minute.